So this section of special cases of linear lines looks at four main things, one being the horizontal line, vertical line being the other, and parallel lines and perpendicular lines. In the last unit we talked about the slopes of all these situations. Now we're actually going to look at the equation of the lines a little bit more. So we know that when we have a horizontal line, we know that the slope of this line is going to have to be equal to 0. So if we were to look at your y equals mx plus b format of the line, the slope-intercept format, we know that we can replace your m with 0. And 0 times anything disappears. So as a result, your y is going to equal your y-intercept. So this is your y-intercept of whatever value, 4, let's say, then you'd have y equals to 4. So any horizontal line will just be y equals to some b value, your y-intercept. Now vertical lines, on the other hand, we know that these ones have an undefined slope, which technically means your m is equal to something over 0. So it's undefined. So that kind of leaves a little bit of a problem in this whole scenario. We've also talked about writing the equation based on a particular value. Let's just call it a, let's say some constant here. So a vertical line, unlike being y equal to a particular value, in this case here it's going to be x equals to a particular value. We can't really use this format of the line because there's no slope, it's undefined. We end up having a big problem. Now in parallel lines, we are going to have two lines that have the same slope. We've talked about that already. So when we have parallel lines, we need to make sure that they have the same slope. Which means if we're given two lines, y1 equals to something and y2 equals to something, your m will be the same. These two values, your m's are going to be the exact value. The difference is your y-intercepts have to be different. This one has a y-intercept down here, this one has a y-intercept up here. So these two definitely have to have different y-intercepts in order to be parallel, but the same slope for them to be parallel lines. If the y-intercepts are the same, the line basically lies on top of itself. There's two lines right on top of each other. So the y-intercepts have to be different and it has to be the same slope. When you have perpendicular lines, let's say these two right here are perpendicular, then your first line will have one slope, oops, x, and your other line has to have the negative reciprocal of that slope. So key thing here is whatever the slope is for the first one, you take the negative reciprocal, times it by -1, and negative, and divide it by 1. Then you're going to get the negative reciprocal. Now the slopes have to have that property, but the y-intercepts, they could be the same, but not necessarily. These two have two different y-intercepts. So there's no way of saying what the y-intercept is going to have to be based on them being perpendicular. They could be the same, they might be different. So y-intercept could be the same, but not necessarily. Whereas the slopes are your negative reciprocals. First type of example we're going to look at that falls into this unit is determining a line, an equation of a line, that goes through two particular points. Now we can find the slope quite easily by using these 2 points. We know that we've got our y2 minus our y1 all over x2 minus your x1. So we're using everything from last unit that we have to work with. So let's say we start with -7, subtract your -3, and -5, subtract your +2. We know that subtracting a negative is the same as addition, so negative 7 plus 3 will give us negative 4, all over negative 5 minus 2, so negative 7. A negative over a negative makes it a positive, so there's our slope. Now, unlike last unit, this is where we'd stop. We'd find the slope between those 2 points, and that was it. Now we actually have to find the equation. So there's a couple different formats we can use. We can either use the slope-intercept format or the slope-point format. Now, given that we have a slope, we can plug that in for either of these two m's. Now the next thing to decide is, well, how do we figure out which one to use from this point forward? Well, the advantage of this one is they do give us 2 points. So, if I use the point slope one, I can choose either one of the points. Let's say I choose this one here. If I subtract my minus 3, that makes it plus 3. 4 over 7, x minus 2. That's the format there. That's complete. So that's one way of doing it, just by using slope point. If I wanted to use slope intercept format, I could actually plug in a point for x and y, either of these two that are given, and solve for my b value. So I could say, let's say if I use the same point, negative 3, 4 over 7x, and x in this case is 2, plus b, and solve for my b. Negative 7 is going to become 8 over 7, plus b. Isolate for b. Negative 3 minus 8 over 7 equals to b. And get my common denominator. Negative 21 minus 8 all over 7 is equal to b. And keep moving on over. And then I'll have negative 29 over 7 is equal to my b. So I can then write my equation as y equals 4 over 7x minus 29 over 7. So that would be my slope-intercept format. Another thing I could do is, I could work with this format here, distribute, combine like terms, and then I get to the same thing. So either way, I can use one of the two formats to figure out either what my y-intercept is, if I don't know what it is, and use my slope-intercept format, or I can use my slope point and come up with an equivalent statement. And again, using either of these two, if I had to leave my answer in a general or standard form, I can then eliminate my denominators, isolate for my constant, or isolate for equal to 0, and go from there. So by starting with either of these two formats, given that I have a slope and 2 points, I can use either of these to carry through and get all the way to standard or general form, depending on what the problem's asking me for. If they just want to find an equation in any format, either of these two would be sufficient for your answer. Another type of example that we'll be seeing is determining whether or not two lines are parallel, perpendicular, or neither. Generally, you'll get something in a standard or general format, and you have to figure out if they are parallel or not, or perpendicular or not. This all depends on your slope. So, being able to convert an equation in this format into either slope-intercept or slope-point is kind of important. The easiest way is to do slope-intercept, because for slope-point you actually have to identify a factor, which is not as easy because there's infinitely many points on a line. So if we're given two equations like this, we can convert these into slope-intercept. So that would be your first approach for both the two lines. And then we can analyze the equations to see if they have the same slope, a negative reciprocal slope, or whether or not they have neither of the situations. So let's look at equation number 1 first, and let's work with that one. So I've got 4x minus 3y equal to 6. I want to isolate for y because I want it to get into y equals mx plus b. So I can move everything over. In this case, I'm going to move my 3y over to both sides. So just to make it positive. So I'll have 4x is equal to 6 plus 3y, minus 6 on both sides. And I'm just going to switch their sides here, so I'll have 4x minus 6. I still haven't got y isolated yet, so I divide by 3 on both sides. y is going to become 4 over 3x minus 6 over 3, which reduces down. So y equals 4 over 3x minus 2. That is my first equation. My second equation, 4x plus 6y is equal to negative 3. Again, I want to isolate for my y variable. It's positive on this side, so I'm going to minus 4x to both sides. And I'll get 6y is going to equal negative 4x minus 3. I want to get y by itself, so I want to divide by 6 on all sides. Then I'll get negative 4 over 6x minus 3 over 6. Now in this case here, again, this reduces, so I'm going to get y is going to equal, if I divide this by 2, negative 2 over 3x, and if I divide this by 3's, 1 over 2. That would be my second equation. The next thing I want to look at to see whether or not they're parallel or perpendicular are their slopes, because that ultimately is what counts. So, looking at these two things, yes, one is negative, one is positive, but they are not negative reciprocals of each other. So, as a result, we're looking at neither in this case. The two slopes aren't the same, they're not negative reciprocals of each other. That's it. The y-intercepts really don't come into play. So there's no need to look at those in terms of determining whether they're parallel or perpendicular. It's just where it's hitting on the y-axis. It doesn't actually determine whether they're parallel or perpendicular.